Okay, let's continue our discussion about phase changes. In the last vodcast, we started calculating the amount of energy it took to raise the temperature of a substance when that substance was in the same phase. And we used Q is equal to mc delta T. So if you looked at our phase change diagram, what we did was calculated the amount of energy to raise the temperature of water, say from 25 degrees Celsius to 75 degrees Celsius. Well, now what we want to do is calculate how much energy it takes to go through the phase change from solid to liquid and the phase change between liquid to gas. To do that, we need to introduce two new terms, the heat of fusion and the heat of vaporization. Heat of fusion and heat of vaporization are constants that we use in calculations to calculate through phase changes. They have the symbols delta H of vaporization, delta H of fusion. And you can see the values are given in either kilojoules per mole or joules per gram. And that's just done out of convenience. You'll find that some calculations, those units will be more convenient. In other calculations, those will be more convenient. Heat of vaporization and heat of fusion are constants for particular compounds. For example, these two are for the compound water. So if we were using, say, ethylene glycol for the problem, we would need different values for heat of vaporization and heat of fusion. What these values represent is the energy required to go from one phase to another. So for example, when you're talking about going from liquid to steam, you're going to use delta H of vaporization in your phase change. You would use delta H of fusion when going through the solid to liquid or liquid to solid phase change. The equation that you're going to use is Q is equal to delta H times the mass. What you're going to notice is that there's no delta T involved, and that should make sense because your temperature is not changing as you're going through that phase change. So let's take a look at our graph and talk about that here. So let's say we were raising the temperature of water from, say, 50 degrees Celsius, and we were trying to calculate how much energy it would take to raise that temperature to boiling point, boil off that water, and then calculate it up to, say, 150 degrees Celsius. Let's say we're talking about 100 grams of water, and that's our initial temperature, and that's our final temperature. What you're going to need to do is a calculation for each section. In other words, that section we would use Q is equal to mc delta T, and our delta T would be 100 minus 50. Whoops, 50. In other words, there's 100 degrees, there's 50 degrees, so we're going to calculate how much energy it takes to go from 50 degrees to 100. We would put our mass, our specific heat, and we would calculate Q. Then what you would do is calculate Q is equal to delta H vaporization times the mass. So we would put our value for delta H there, our 100 grams there, and we would get a value for Q. And then we would calculate Q is equal to mc delta T for steam, and now it would be 150 minus 100. Now the one thing that we're going to point out, well, two things we're going to point out. Once you have your values for Q for the three sections, you would simply add the three Q's together. The other thing that we're going to talk about when we do some of these, actually do the calculations, is your specific heat value is going to be different for steam than it would be for water. And it's also different than for ice. Okay, first let's address this question. Which would you predict would be the larger value, delta H of vaporization or delta H of fusion? And if you were to look back at the first slide, you already know what the answer is numerically, but then explain why. Okay, we know the delta H of vaporization is larger. The question becomes why. Think about it. If you had solid ice and you were trying to make it into liquid water, what do you have to do to the molecules from the solid to get them to the liquid? You simply have to break apart that structure, in other words, that crystalline structure of water molecules. You have to get that crystalline structure to break apart so those molecules flow past one another. However, if you're going from the water phase or liquid phase to the gas phase, then you've got to get those water molecules much further apart. In other words, you've got to break those hydrogen bonds so those water molecules are much, much further apart. So from solid to liquid, you're just getting that crystalline structure to break apart into a liquid phase, but the molecules aren't leaving the system. From liquid to gas, though, those molecules are actually leaving the system and flying around as individual water molecules. So that's going to take much more energy to do than it would to go from solid to liquid. Okay, I mentioned earlier that specific heat for solid, liquid, and gas for water are 3 different values. And as you can see, the specific heats for solids and gases are just about the same, and for liquids it's a little bit, well, I shouldn't say a little bit, it's quite a bit higher. So when we're doing these calculations, you want to use those values in your calculations. Okay, so let's do an example problem here. It says, how much energy does it take to raise 34 grams of water at 50 degrees Celsius to 125 degrees Celsius? So we're going from the liquid phase to the gaseous phase. So we have to calculate that value. In other words, from 50 degrees to 100 degrees. We've got to calculate the phase change, and then we've got to calculate from 100 degrees to 125 degrees. So we need 3 calculations for Q, and then we're going to add up those 3 values of Q. So for the first one, we've got Q is equal to 34 grams, 4.18 joules per gram degree Celsius, and we're going up to 100 degrees from 50 degrees, and that's degrees Celsius. So let's do that calculation first. We have 50 times 4.18 times 34, and we get 7,106 joules. Let's do the calculation for the phase change. So remember, we have Q is equal to delta H of vaporization times the mass. So delta H for vaporization for water, if you remember, is 2,257 joules per gram. We'll put that in, 2,257 joules per gram times our mass, 34 grams. Do the math. 2257 times 34 is 76,738 joules. And let's do the third calculation from 100 to 125. So Q is equal to MC delta T. So Q is equal to 34 grams. Now our C value for steam, if you remember, was 2.09 joules per gram degree Celsius. And I should have left myself some more room here. We're going from 100 to 125. So let's do that math. We've got 25 times 2.09 times 34, which is 1,776.5 joules. So then we're simply going to add together that value, and that value to get our final answer in joules. Let's take a look at a couple more problems. It says, how much energy does it take to melt 100 grams of ice? So we have Q is equal to delta H of fusion, which is 334 joules per gram, times our mass, 100 grams, so we have 33400, grams cancel, joules. If we were going to calculate how much energy it takes to boil 100 grams, we would simply have Q is equal to delta H of vaporization, and I believe we said that was 2257, I believe, joules per gram times 100, so we have 225700 joules. And as you can see, it takes much more energy to boil the water than it does to melt the water. And you probably knew that intuitively already. So when you're doing these calculations, you just want to remember you've got to do a calculation through each section. So when I do these problems to this day, I always draw that little diagram. And I know I need a calculation for that section, that one, and that one. So if I were going from ice to steam, I would have 1, 2, 3, 4, 5 Q values, and then I would simply add those all together to get a final Q value.